And now, finally, we have the Wollaston medallist, Ed Stolper. Why do the interiors of planets partially melt? Very close to my heart, this, so I'm very pleased to do that.
I want everybody to whom I've asked the question, how do you pronounce Wollaston, to know. He just pronounced it Wollaston, which is how it's pronounced for the mineral, wollastonite. Okay, so I'm going to talk about, it's late in the day, most people, although I want to note that all four of the speakers will have talked about igneous geology in one way or another, so I don't have to, I guess, explain why it's important. And I took out the slide that had that anyway, so it's okay. We're going to talk about some very simple aspects of igneous petrology, mostly because it's late in the day, and I'd like you to try to remember something of the talk, and it's sort of a technical topic. And so we're going to try to get some simple principles out that also, in some cases, relate to our everyday life that I think you'll be able to understand. But it's obviously a very important process, igneous activity, in terrestrial geological processes. Here's a volcano from Costa Rica. But it's also, very important in the solar system. And in my introduction, in my acceptance, we talked a little bit about that. But there's igneous activity, these are all rocky planets, on pretty much every planet. We actually have samples from the Moon, from this asteroid Vesta, and from Mars. By remote sensing, we know a fair amount about what's going on in Mercury, although some people believe we have samples from Mercury, believe it or not. There are some meteorites that are claimed to come from very high pressure that they can come from the interior of Mercury. I don't believe it, by the way, but some do. Io, the most active igneous body in the solar system, with its volcanoes you can see here, and the colors are due to sulfur from the volcanism. And Venus has volcanic activity that you can see. So it's all over the place. It also has other implications on the Earth. It's probably the origin of the atmosphere. It may be playing an important role in extinctions. It's important in ores, as we've heard a little bit about. It's also important simply as a marker for working out geological history and processes. But the first question is, how do magmas form? We'll do this very quickly because it sets up the simple set of problems I want to talk about. So first of all, we know from geophysics that most of the mantle is solid. So it's not that there's big hunks of melt down there that are just waiting to come out. There are localized regions, again from geophysics, that we know have small amounts of melt in them, a couple of %, but they're localized in places where we expect it. That is largely where we have magmas erupting. Based on a variety of constraints, the Earth's mantle, and the interiors of all the planets, pretty much, all the rocky planets, are peridotitic. They're rich in olivine and pyroxene, compositionally and actually mineralogically at low pressures. Most magmas on the rocky planets are basaltic. This is actually a simple and obvious result of the fact that most of the mantles of most of the planets, the rocky planets, correspond to something close in condensed elements to the sun, and they are peridotitic. And if you take and melt a peridotite, you're going to get basalt. Lots of different flavors, things you can study, but basalts are going to be the dominant thing. And also experimental petrology and geochemistry suggest, probably indicates, more appropriate, that basaltic magmas, that is these things that are on all the planets, are generally produced by a few tens of % of partial melting of mostly periodic sources. We've heard about partial melting from two of the previous three speakers. And here's a statement that we're going to explore in some simple terms. Basaltic magmas are generally produced by partial melting of the Earth's interior. So the questions we're going to look at are, why does the mantle melt? And why does it melt partially? And the answer to this question, which we'll get to at the very end, is related to what you think the important variables are in the process that leads to melting. So that's why does it melt? And then we'll be able to address why does it melt partially. Now, just to set this up, we mostly think, and most of the diagrams I'll show, or some of them anyway, but we mostly think in terms of pressure and temperature. Those are the variables we want to vary. We vary them experimentally, we vary them in our lives. And when you take a material and you control the pressure and the temperature and the composition, You reach equilibrium when the Gibbs free energy is minimized. And most of the diagrams that people use to teach petrology are pressure and temperature and composition and Gibbs free energy. You're mapping out what is the lowest Gibbs free energy. So we tend to think that the controlled variables are pressure and temperature. One of my main points is going to be that the controlled variables during melting are typically not pressure and temperature. They're the ones we want to think of, but they are not the right variables if you want to understand the process. And once you understand those variables, you'll understand why partial melting occurs. And we're going to do it, we'll see how successful this is, with some analogies that, again, we encounter in our everyday lives that might allow you to understand a little better than if we just did it with diagrams or equations. So, I do this experiment all the time. It's a good way to break the ice if you're talking to a physicist or an astronomer or a mechanical engineer, a biologist. So why do you think? They say, what do you do? Well, I'm an Igneous petrologist. They don't know what that means. You say, well, think of Hawaii or something. Why do you think that magmas have formed to come out in Hawaii? Now, it's either a great secret we've kept, or it's because the main reason is not something that happens in our everyday lives, or that they've just never thought about it. And the usual answers, I actually did when I was preparing the talk. I went to lunch with an aeronautics engineer the other day, and I said, "How do you think you produce these magmas?" And he came up with the obvious answer. Well, you heat something up and melt it. You apply heat. You put energy in. That's how we would mostly melt things in our everyday lives. He also stopped and said, well, maybe there's just a lot of melt down there all the time. It just comes out, all right? So for us, we all sort of know the answers, but it is not a it's not common knowledge. Okay, so it's not a trick question. You would add heat to it. And there's a variety there's a list. Basically, you add energy, all right? Heat is the most convenient way, but not the only way. One is a Bunsen burner. You put it on the stove. You put something cold up against something hot. Heat flows from the hot to the cold, and it heats it up, and eventually will melt it, whatever it is. All right? This turns out to be important, people think, in the generation of continental flood basalts, and also in the partial melting due to contact metamorphism, if you like, at the margins of plutons. Another way that's potentially important, which is energy addition, is deformation and shear. People think that at some level, some people think it's the majority, some people think it's the minority. Generation of island arc magmas is due to addition of energy that causes the materials to heat up. It's definitely important in pseudotacholites. These are melts that produce at fault zones, and also the tidal heating of Io. Another way is radioactive heating. Obviously, you heat things up. It generally operates, and that's what's driving the whole engine, but it operates in long time scales, except that picture we showed of Vesta, that asteroid, that's thought to be due to primordial aluminum-26, which has a very short half-life, so you deliver a lot of radioactive energy very, very shortly, and that body melted at about 4.5 billion years ago just from radioactive heating. Impact. Generally, this doesn't lead to partial melting. You put so much energy in that you melt it fully. Induction, we don't think about this, but this is if you have magnetic fields in the solar system, you can generate currents inside of a body, and so melting of asteroidal bodies and all these bodies early on is possible. And then lightning, this happens. You get these things called fulgurites. Maybe no one's ever heard of them, but they are places where lightning is struck and it melts, and you have glass. And also conjules and meteorites are thought to generate by lightning, and also solar heating, perhaps the surface of Mercury. Now, although there's a long list here, let's give the one example. It's not the dominant mechanism we're going to see, but it is important. And here's a cartoon for continental flood basalts where you have a plume that comes up, and it doesn't come up all the way. It's stopped by the cold lithosphere. It's hot. That's why it was buoyant in the first place, perhaps. And it stops, and either you just get straight conductive heat flow into the lithosphere leading to partial melting, or more importantly, you have advection of heat, probably by liquids that come from the hot stuff, come up here and heat it up and melt it. So, heating is one way. We're going to set that aside. We're going to come back to it in terms of how to think about it, but it's the obvious way. But it's not the only way in which in our everyday lives we melt things. And There are another 2 ways I'm going to go about, I'm going to explain, and one of them is of these things that we melt things in our everyday lives of considerable importance in the generation of magmas within the Earth. So, you know, when I was a visitor at Cambridge several years ago, it was really cold, and the river froze over, and there was snow, so I assume that many of you can answer this question. After it snows, and you get ice on the walkway, how do you melt it? You do not have a flamethrower. That you don't do by adding heat. You have something else you do. And what do? You put salt on it. And so this is metasomatism. You're changing the composition, and it leads to melting. So this one, here we're going to have a little diagram. We're going to do this related to something that, if you ever make ice cream, you know about this diagram. If you do work on melting the ice on your street, you use this. And I'm going to bring it back because Dan McKenzie's here. If you are an avid gardener, you will observe something related to this. I observe it all the time. I'm not as avid as others, but I do observe this. So all you do, here's the diagram. This is pure water. This is pure salt. There's a break in here. So this is salt. This is ice. This is salt. What this shows you is that this is temperature. If you're below 0 centigrade, or if you like Fahrenheit, it's over here someplace, 32, it's ice. All right, so now I got ice on the walkway. Now over here is pure salt. It melts at 800 degrees centigrade, okay? There is what's called freezing point depression. This is eutectic. Here, at this single temperature, at 1 atmosphere, I have ice and brine, salty water, and salt that coexist. So what happens, if you don't know how to read these diagrams, I'm not going to explain it, but you should be able to get it intuitively, and you're all geologists, you've been trained at some level in this. You may have forgotten, but you once knew. Okay, so by the way, notice the temperature is the critical variable. We're going to see in a moment, it's sort of a mistake. So imagine I start with ice, and then I dump in some salt. So the composition moves to the right. Even infinitesimally moving to the right, it's going to be on a tie line between ice and salty water. So let's add more and more ice. When I've added enough so that the composition's here, I'm going to be 50% ice and 50% water. Once I get to this point, I then move into the water field. I've got it melted entirely. All right? So that's how it works when you want to melt the ice on your street. You add some salt. Okay? You don't add this much, by the way. At least I don't think you do. You add just to get it partially melted. Okay? Now, that's the change in composition that leads to melting. We call this metasomatism. We could have just used this. I use that example because I'm coming back to things that I hope you can understand from cooking. This is the albite water system instead of the salt water system. And here is pressure versus temperature. If I have albite with no water in it, it melts along here. All albite, heat, crystalline albite, molten albite. If I add water, this eutectic temperature, it goes down and down and down. So you get an enormous decrease in the temperature which melting is required. Here at 5 kilobars, it goes from about 1125 to about 725. That's a big decrease in the temperature just by an infinitesimal amount of water. But we could have drawn the same diagram. So at 5 kilobars, here's temperature, here's the water content. So this is pure albite, this is pure water. At 900 degrees, I'm crystalline. So all albite, but I add a little bit of water, and now I'm in the field of albite plus liquid. And so I add more and more water, I get more and more melting until I get complete melting. All right? So this would be metasomatism that increases the water content. You can do it in almost any change in composition, but obviously fluids are an easy way to do it. So now how should we be thinking about this? I set up a timer, but it seems to have stopped, so I hope somebody's been paying attention because I haven't. Okay, so here's a cartoon that shows why this is important. I have oceanic lithosphere going down a subduction zone. I dewater the crust. I have metamorphic reactions, generate water. The water then comes up. It's not only pure water, it's not pure water, but the water comes up, and it does precisely what we just described. Something that was solid, because I added the water to it, it starts to melt. All right? What happens after that? The regions probably rise and things happen. We'll get into that a little later. But this is very, very important in the geochemistry of island arcs, geochemistry of continental margins, the existence of magmatism and so forth, and it's also true in the back arcs, is almost certainly due to this kind of process. Okay, these diagrams are harder, but let's don't look at them yet. I'm going to tell you the story for Dan. Okay, so do they have Miraclegro in this country? It's this stuff that's sort of greenish turquoise or whatever. It's a liquid fertilizer. I strongly recommend it because you can't burn the plants. That's the main reason. And so what you do is it comes with a little plastic cup container. Imagine the beaker. And you pour the greenish powder in. And then you pour water into it. All right? And then you screw the top on. You squirt it all over the place. Now, has anybody ever done this? Okay, and what do you notice when you have your little plastic conical, it's not a beaker, it says an angle. When you pour the water onto the green stuff, what happens? It what? It gets cold. It gets strikingly cold. And actually, this weekend, I went and did the experiment. How cold does it get? All right, so I went and took some lawn fertilizer. I put it in my little container. I actually used the plastic container it came with. From work, I borrowed a good thermometer, meaning it wasn't at 1,000 degrees. I could measure temperatures at room temperature. And I did the experiment well. I left the powder sitting on the kitchen counter and my water sitting on the kitchen counter so they'd be at the same temperature. So I wanted to add it at the same temperature, just like we said with the melting. I stuck my thermometer in the middle, then I poured it in. It started at 68. Oh, do you want to do Fahrenheit or centigrade? Centigrade, okay. It started at 20. By the way, both were on my little scale, so I didn't even convert it. So it started at 20, and then within a second or two, it was at 1 degree centigrade. That's why it feels so cold, by the way. So what, because that is cold. I never knew it was that cold. I would have guessed it went down by 5 degrees. All right? So what is going on here? What we're doing is we're doing this process of taking, this is the same thing we had before. We have something that's solid. Unfortunately, it's inverted, but this would be the green stuff, I mean the Miraclegro. It's at a certain temperature. It's solid. I then add water at the same temperature, and what happens is the temperature goes down. All right? And why does that happen? It's because in order to melt something, I have to add the heat of fusion. To change something from a crystal to a liquid, when I change ice to water at 32 degrees Fahrenheit, I have to add a lot of heat to melt it. That's called the latent heat of fusion. Now, in the process of my Miraclegro, I pour the water in, and it melts much more rapidly than any heat can diffuse in from the outside world. So it's a process in which temperature is not controlled. What is controlled is I mix them together rapidly, and the enthalpy, the heat content, the entropy actually true, because it's close enough to irreversible. The heat content, that's what it's called, even though it's a misnomer, the enthalpy, is constant, and yet I have to melt it. I have to melt the green stuff to get it into solution. So I provide the latent heat of fusion, but there's no heat coming in. So where does the heat come from? It comes from cooling the stuff down. I cool it down, that releases heat, which then goes into the latent heat of fusion. And it's a big effect. So here's the first place we see that, although it was easy to describe it this way, as adding salt to water at constant temperature, what really happens is if I added my salt to the water, if I'm making ice cream or if I'm doing this thing with a fertilizer, and the enthalpy is constant, the temperature goes down. It goes down to the freezing, to this eutectic, and then if I add more and more water, it stays along with this. Eventually, it goes back again to the salt, which has the same temperature. If I take something started at a higher temperature, instead of starting at minus 15, I start at minus 8 or something, whatever it is, it goes down further before it reaches this temperature. So the main point is, if I want to understand this process of making ice cream, because when you do ice cream, you mix salt, ice, and salt, and guess what happens? It goes to zero Fahrenheit, or whatever it is, minus 21 centigrade, and it stays there. So the point is that temperature, when it reaches equilibrium, is well defined, but it is not what we control. What we control, if we do it fast enough so heat can't get in and out, what we control is the enthalpy. Okay, and then when we want to melt, if the enthalpy is constant, I've got to get that latent heat of fusion from someplace so it cools down. Okay, this, by the way, I'm not going to go into it. This is the right diagram to use. I can, by the way, keep it at constant temperature. What do I have to do? When I add my salt, it wants to go down, I then have to add heat to it. So in order to keep it at constant temperature, as I add salt, I have to sort of have a little flamethrower on it to heat it up, to keep it to the constant temperature. So I can work, but it's not, the temperature is not the naturally controlled variable. The enthalpy is. Okay, so that's it for metasomatic melting. That's also not the dominant. The dominant one, we all know, and go do an experiment. Ask a physicist. And it's not that they don't know, they've never thought about it. We got an astronomer here, he can tell us if he's ever thought about it. Decompression melting, and it's been mentioned a few times, is something that we don't experience. Okay, so the main way in which things melt is you start with something that's buoyant, and this is a cartoon. Obviously, I've got something from someplace, and I drew my ocean island on it. But we have material that ascends under ridges. We have material that ascends under an ocean island. And after that initial bit of melting, we have material that ascends here. So that was when I was supposed to finish. I'm not that far from being over, so we're fine. Okay. By the way, I had another 10 minutes. I set it up with 10 minutes to spare. So don't feel like we should be leaving. You got a couple of minutes. Okay. Okay, so what is the process here? Now that what are the variables that happen here? Well, obviously, as something rises, the pressure goes down. So pressure is a variable that's controlled, but it's temperature controlled. And the answer is no, and we'll see why in a moment. It's the same, very much the same explanation. But what is the variable that's being controlled? Now, if you think about it, melting occurs, let's say, in the upper 100 kilometers, just making that up. As I come up and I start to melt, and I melt in in the upper 100 kilometers, how long does it take a parcel of mantle to traverse that 100 kilometers? It takes about 1 million years, making a 10 centimeter spreading rate. It's a little fast. How far does heat diffuse in a rock in 1 million years? It's about 5 kilometers. So as long as your parcel of material that's rising is bigger than 50 or so, it's not going to be affected by any heat coming in or out. So this process is one, just like when we dump the water into the Miraclegro, where on the timescales are important, no heat flows in or out, it's adiabatic. But it's more than adiabatic. It's adiabatic and roughly reversible. And that means that if I took the heat back out, I'd go back to the same place. And it's pretty close. And so if you have something that is adiabatic and it's reversible, the entropy is constant. And so, this is not original to me, Mike and Dan, lots of people have written papers on this, but it's not entirely well known. And even petrologists, they like to call it adiabatic. And I've put on isentropic and say, why is it isentropic? Well, it's adiabatic, but it's a particular kind of adiabatic, and that is reversible. Okay, so the right variables here are pressure and entropy. Pressure is going down as the thing rises, but the entropy is being held constant. So this is sort of easy to understand why you get melting. Here then is temperature and pressure. You just can't get away from it. You start, and this is diopside. So this is the solidus. Below here it's solid diopside. Above here it's liquid diopside. We start here, and we have it ascend, and it comes up. Notice that the temperature isn't constant. Even when there's no melting, the temperature goes down a little bit given the thermodynamic properties of diopside. So curiously, it's cooling, all right? And then it runs into where the diopside wants to melt. Well, what happens is, as I take a decrement of pressure along this curve, all right, and then it'll continue along that curve, start here, and then have it melt. Well, what's going to happen? No heat flows in or out. I have to provide this latent heat diffusion, so what happens is it pops onto this curve. You melt adiabatically or isentropically by coming along, you melt. It's nothing about the properties of diopside in particular. It's because you run into the solidus. Okay, so it's a real heterogeneous phase equilibrium issue. But then when melting takes place, the temperature goes down, and because you have solid and liquid diopside, it has to stay along here. So the main reason that melting takes place, and by the way, to get it to melt completely, I would have to cool by several hundreds of degrees. All right, so this is a big effect. All right, and so you come along, once it melts, you start to cool. So in contrast to the intuition of everybody that you make something melt by heating it, it melts and cools at the same time because of the independent variables you've chosen, pressure and entropy. Okay, so temperature's changing. It has a well-defined value, but although we like to think about it as the important variable, it's dependent. However much I change the pressure, keeping constant entropy, temperature will find a place where it belongs at equilibrium, but we didn't control it explicitly. Okay, now here's a set of diagrams which some of you won't be familiar with if you aren't. It's a little hard, but the right way to do it, instead of plotting pressure versus temperature, which we are all want to do, and then it comes the same thing. I've switched the the directions of them. I take something adiabatically, it comes down, and then it goes along here, melting and melting and melting. What we should do is plot in terms of the correct variables, pressure and entropy. Now, by the way, on this at equilibrium, Gibbs free energy is minimized. In this, the enthalpy is minimized at equilibrium. And now we can read off easily. Here's the solidus, here's the liquidus. Now decompression is just a vertical line because entropy is constant. And as I move down, I start to melt here. When I reach here, where it's halfway between the solid and the liquid, it's 50% molten. When you reach the surface, it's about 30%, 90% of the way along, and so it's 90% molten. And now we can read off of this diagram. Here's the temperature. I can see how much the temperature is changing. And you follow it in both of them, but this one is very informative because those are the variables you've controlled. Okay, there's lots of things you can do with this. One interesting one is that if you look at this, stare at it for a while, when you have something rising up, per decrement of pressure, it melts a lot less deeper than shallow, and you can see that here. It goes from 0% to 50% melting. When it went from 70 kilobars to 20, it goes from 50 to about 100% melting, 90% melting in the next 20 kilobars. This is a consequence of this choice of variables. Okay, I think that now to the question, why does it melt partially? The textbook's answer is right, but it misses the point that I want to make. The textbook answer is this diagram, first done by Bowen and Shirer, probably. And so forced right phaolite versus temperature at some pressure. It's olivine down here, liquid up here, and then there's a loop. The tie lines are horizontal because when I have melt and olivine coexisting, they have the same temperature. And you can read about it in any textbook. The reason you get partial melting is if I now heat this up at constant pressure by adding heat to it, I have this interval between the solidus and the liquidus. All right? And so I will always get partial melting. But what we see here is you get partial melting even if it's only one component system. It is not, it's the process that does it. It's not this contributes, by the way. No matter what process you chose, you will get partial melting because of this. But this shows you it's not, it really depends on the variables that you choose. And it also is very well illustrated by the topology here. This diagram, melt, one phase, melt, olivine plus melt, olivine. Melt, diopside plus melt, diopside. These two diagrams look very much the same. And why they look the same is they have a region, one-phase regions with horizontal tie lines, and a one-phase region. And now if I sort of close my eyes, let's see if this works, and I want to be within this, okay? I take random places. Are they all getting inside there? Sort of? Close enough. I can choose these two variables independently, and I can get one phase or two phase. If I go back to the previous figure, if I did the same thing here, I can never get two phases. All right? So it's a choice. The point is that you're plotting a variable that is the same in both phases versus one that's different, a variable that's same against another one that's the same. So this is very, very deeply embedded in the process and the thermodynamics. Okay, so I think that that's it. That's it. So magmas are generated in planetary interiors primarily by asymptotic decompression melting, but also metasomatism and or addition of energy. These two, this is most important, second most, third. Decompression has a curious feature that melting is accompanied by significant cooling. It's not odd, but it's odd to people who haven't thought about it, reflecting the constancy of the entropy. Melting due to metasomatism may also be accompanied by significant cooling. By the way, I can get myself out of this in certain physical by imagining the source regions in other ways. The mantle invariably melts partially, although it's generally attributed to the multi-compositional nature of the source, it's actually intrinsic to the process. And my main point is when you're thinking about any of these things, it's critical to specify the independent variables. And in fact, although we like to think about pressure and temperature, in geology, temperature is usually a dependent variable. It related to the amount of heat you're bringing in and out of the system, and that's what controls where you are in a particular place. So that's it. Thank you very much, and thank you again to the Society for the honor.